Entanglement is a quantum correlation which is useful to most quantum technologies.
There are two parts which sort of behave in a correlated manner. Because of this effect of environment, errors come in. Very quickly, their coherence will be gone.
In our lab, over the last several years, we have been studying several schemes, both experimentally and theoretically, for preserving coherence.
A study led by RRI has uncovered a unique relationship between a lesser studied form of entanglement and noise.
When two spatially separated particles get entangled with each other in a single degrees of freedom, you are sending one bit of information. But when two different degrees of freedom of the same particle get entangled, then you are sending actually 2 bits of information. So you are doubling the information. That is the advantage of intraparticle entanglement. Addressing each degrees of freedom individually is challenging. There are surge of theoretical ideas for various applications of quantum computing, quantum communications, quantum information processing tasks, but we found that there is no rigorous analysis of decoherence study for the intraparticle entanglement under environmental noise.
Our study lays down the general framework for decoherence in intraparticle entanglement.
There we found counterintuitive results.
See, honestly, we could not believe it in the beginning.
To our surprise, we find that intraparticle entanglement is more robust to certain kinds of noise than its more popular interparticle counterpart. We have been able to show that noise can actually be our friend. We can use noise to create entanglement when initially there was none. Even if the entanglement interacts with the environment and goes to zero, we can use noise to revive it. And finally, we have found a beautiful geometric interpretation for concurrence, which otherwise tends to be a rather abstract mathematical construct. A next step would be to apply this to specific physical systems. In our lab, we are already working on an experiment using single photons to study some of the ramifications ourselves. This work has been largely supported by the ITPAR grant and more recently the National Quantum Mission of the DST.